So we have a problem here. We have a current source that has a value of 10 e to the minus 5t amps for t greater than or equal to 0 and 0 otherwise. And I want to find the voltage, the current, the power, and the energy. It says find the current, but you're given the current. So it's actually find the voltage, the power, and the energy. So V of t equals L di of t dt. So it's going to be 0.1 times the derivative with respect to time of 10t e to the minus 5t. Okay, the derivative of 10t e to the minus 5t is 10 e to the minus 5t minus what? Ten e to the minus 5t minus what? It's going to be a long quarter. Oh, I got to start calling on people. That's how we fix that. I'm about to call on Smiley. As soon as I figure out what Smiley's name is. Where is my folder? Smiley might be saved. I think I left my folder in my office. Yes, but it's minus. It's minus 50t. You're saved this time, Smiley. 50t e to the minus 5t. Okay? So when I divide that by 10, I get that my voltage is e to the minus 5t minus 5t e to the minus 5t volts for t greater than or equal to 0. Okay? Questions? Questions? Any questions? All right, I want to find the power next. So the power is going to be P of t is equal to V of t times I of t. So that's going to be e to the minus t minus 5t e to the minus 5t times the current, which was given in the problem statement as 10t e to the minus 5t. Okay, what is the power for t greater than or equal to 0? So that would be 10t e to the negative 10t minus 50t squared e to the negative 10t. This is for t greater than or equal to 0. What are the units for power? Bless you. What are the units for power? Watts. Okay, that's watts. Okay. So what you should see here is that when the inductor is charging, I have a positive slope. When the inductor is discharging, I have a negative slope. And what happens with that is I see my voltage go from a positive to a negative number, which makes sense because derivative is slope of the tangent line. So my power is also going to go from positive values to negative values. My power is going to also go from positive to negative values. Remember from DC circuits, when the power is less than 0, the device is delivering power, or the inductor is releasing energy back into the circuit. And when the power is greater than 0, the inductor is absorbing power, or charging or storing energy, right? So power less than 0, delivering, power greater than 0, absorbing. Inductors and capacitors store and release energy. So that's what's happening here. So if I multiplied these two figures together, we won't do this. You'll see that they have a positive half and a negative half, which represents when this is happening. Questions? Okay. And lastly, we want to find the energy. The energy is 1/2 C V of t squared. 1/2 C V of t squared is 1/2 times 0.1 times the voltage, e to the minus 5t minus 5t e to the minus 5t squared. Oops, sorry. Anybody notice I did the wrong formula? Y'all ain't paying attention no way. You don't care. I think Josh is, though. Okay. 1/2 L I of t squared. So it's actually the current. And the current is 10t e to the minus 5t. Sorry about that. 10t e to the minus 5t squared. It's 1/2 L I of t squared. So it's 1/2 times 0.1 times the quantity 10t e to the minus 5t squared. So the energy is 5t squared e to the negative 10t joules. 5t squared e to the negative 10t joules. Are there any questions? How's everybody doing? Do you feel like you're still being reviewed? Or is this totally new for you? So you're just not going to answer me? Is that how we're going to play it? Smiley, do you feel like you're being reviewed? Okay, good. How did you know you were smiling? I love it. All right, page 4, page 4. So a capacitor. A capacitor is an electric component that is made up of two conductors separated by a dielectric or an insulated material. And it's the only device that is similar to a battery that can store electric charge. So it can store electric charge or store voltage and then release it back into the circuit. So just like an inductor, no power is dissipated in the ideal capacitor because it's going to store energy and then at some later point release it back into the circuit. It has a time-varying electric field that produces a displacement in current in the space occupied by the dielectric. So capacitance relates the displaced current to voltage. And energy stored in a capacitor can be used and released to fire a flash bulb. So the example I gave the last class is when you buy those recyclable cameras, like you can get them at a drugstore, and you hold the button down, it charges up the cap, and then when you press the button to take a picture, it will release the flash. Has anyone ever seen that before? They're like these box cameras. I was going to say I don't think people use them anymore, but Serena's daughter had one at the U.S. Open taking pictures. Did anybody watch the U.S. Open? So you don't know what I'm talking about right now. Well, you know what? It's all good in the hood. It's still a good example. It don't matter that you don't know what I'm talking about. All right. Anywho, I digress. What are the units for capacitance? What are the units for capacitance? Farads, very good. What are the units for charge? Coulombs. So there are two ways you can express charge in terms of capacitance, where Q of T is CV of T, which is equal to I of T dt. We use this formula to get to the one that I wrote on the board, where the current through a capacitor is C dV dt. The current through a capacitor is C dV dt. Or the voltage across the capacitor is 1 over C, the integral T naught to T, I of tau d tau plus V of T naught. Okay, so current and voltage for a capacitor. And just like we have on the board, you can also get the power and the energy, where power is V of T, I of T. And the energy is 1/2 C V of T squared. Okay, is everyone good? Let's take a look at another problem. So I'll tell you this one because the instructions got cut off. So we have a plot here of current, charge, and voltage. And we want to determine C. We have a plot of the current, the charge, and the voltage, and we're trying to determine the size of the capacitor. Okay, so the first thing we have is that there is a constant current that turns on at time 0. So the way to think about it is we have a current, it's like a step function, and at t equals 0, it turns on to 1 milliamp. So at that point, my capacitor starts charging. My capacitor starts charging, and it charges up to 5 microcoulombs. 5 microcoulombs. That makes sense because that should be the area under that rectangle. That should be the area under the rectangle, because remember, the relationship between current and charge is that Q of T would be equal to the integral from 0 to T, I of tau d tau. So this is a plot of the area under the curve. That's a plot of the area under the curve. If I integrate a graph, it's the area under the curve. So it's going from 0 to 5 microcoulombs in 0 to 5 milliseconds, and that makes sense. Questions? The voltage to go from here to here is V of T equals 1 over C, the integral from 0 to T, I of tau d tau, I of tau d tau. So what this represents is I've now scaled this graph by dividing it by the value of the capacitor. I've scaled this graph by dividing it by the value of the capacitor to get the voltage. So now, instead of peaking at 5 microcoulombs, it peaks at 2 volts. So if it peaks at 2 volts, what is C? If it peaks at 2 volts, what is C? I have a hint on the dot cam for you. What is C? Tell me your name. In the back. Ben? Ben? Okay, Ben. 2.5 microfarads. And then who's that behind Ben? Brendan and Ben. Okay. It's 2.5 microfarads. Very good. So it's 5 micro divided by 2, or 2.5 microfarads. Okay. Are there any questions? All right. So some of the things I've already reminded you of, but the power for a capacitor, CV of t, dV of t dt, the energy, 1/2 CV squared. Some characteristics of a capacitor are, because the current is 0 under DC conditions, we can model a capacitor as an open circuit, because an open circuit is how we represent 0 amps. Okay. Under high frequency conditions, we model a capacitor as a short circuit. And once we talk about impedance, you will see why. And we call that capacitors and inductors are dual. So they're just the opposite of each other. So if an inductor under DC is a short, capacitor under DC is an open. If an inductor under high frequency is open, a capacitor is short. They're always the opposite. So if the voltage is continuous for an inductor, the current is continuous for a capacitor. I think I said that the opposite. So a capacitor, the voltage is continuous. Inductor, the current is continuous. Okay? So that means that if I was to draw my capacitor charging and discharging, the voltage across that cap has to be continuous. It cannot abruptly change from a positive to a negative number. But when it changes from charging to discharging, what you will see is that the current can change from a positive to a negative number, because it's the slope of it's the derivative. So when it becomes a negative number, it drops. So voltage across a cap is continuous, current is not. Current through an inductor is continuous, voltage is not. Okay. Anybody heard any of this before? Feel like Groundhog's Day? All right, moving on. So work with your table mates or alone if you're not like that kind of person, and solve the problem at the top of page 6. Work with your table mates and solve the problem at the top of page 6. That's right. Okay, so let's talk about why. The answer is 1. So if I have a capacitor voltage like this, and I know that I equals C dV dt, then the derivative is represented as the slope of the tangent line. So the slope of the tangent line is positive, negative, positive. So that means even if I don't have numbers, I know that the shape needs to be a positive number, a negative number, and a positive number. This doesn't work because that's not the derivative, and this doesn't work because it goes to a different value here. Okay, does everyone see why the answer is A, as in apple? Okay, let's try another one. At the bottom of the page, an initially uncharged capacitor. That means VC of 0 is 0 volts, initially uncharged, and it's a 1 millifarad capacitor, so C is 1 millifarad, has a current as shown in the following figure. Calculate the voltage across the capacitor at t equal 2 milliseconds and t equal 5 milliseconds. So since I'm given current and I'm looking for voltage, this is going to be an integral question again. It's going to be V of t equals 1 over C, t naught to t, I of tau d tau plus V of t naught. V of t equals 1 over C, the integral from t naught to t, I of tau d tau plus V of T naught. And when you're given a graph and you have to find the integral, we know that's also the area under the curve, okay? So if I was going to make a plot first, I know that the shape has to look something like this. Because when you find the area of a triangle, it becomes parabolic. And when you find the area of a rectangle, it is linear. So it's going to be something like that when I plot the voltage. But we need to figure out what those values are. How are we doing so far? Who's feeling overwhelmed and wants to leave? Okay. So I of t is 0 for t less than 0. And it's 50t milliamps for t between 0 and 2 milliseconds. And it's 100 milliamps for t greater than 2 milliseconds. Cracks me up. All right, so what we're going to do is let's find the integral. So the integral of I of tau d tau between 0 and 2 milliseconds is going to be the integral from 0 to t, 50 tau d tau. Remember, it's not initially charged. I don't have to worry about anything like that, but this ends up being 25t squared. Does everybody agree with that? (25t squared). But then if I need to divide it by 1/1 milli to make the voltage, I'm going to have 25t squared. And that's going to be in milli. So this is going to be millivolts. So between 0 and 2 milliseconds, 25t squared millivolts. What is the voltage at exactly 2 milliseconds? You can also get this from the area under the curve dividing by 1 millifarad, right? What is the voltage at 2 milliseconds? Yes, Shayna. 100 millivolts, okay? So we should also be able to get that because the area under the curve is going to be 1/2 base times height. So that would be 100 micro. 100 micro divided by 1 milli. So it becomes 100 millivolts. So that means right here is 100 millivolts. Okay, how are we doing? Is everybody okay? It's very mathy in here. It gets mathy in here sometimes. We're okay with that. We're engineers. We do math. That's what we do, whatever your name is. Alicia. My name's Alicia. It gets mathy, Adrian Smiley. It does. All right, are we good? Now let's do the integral from 2 to 5, or greater than 2 rather. T greater than or equal to 2 milliseconds is going to be 1/1 milli. The integral from 2 milli to t, 100 milli d tau, but I have to add in the initial voltage now, which was 100 millivolts. I have to integrate for t greater than or equal to 2 milliseconds, 1/1 milli, the integral from 2 milli to t, 100 milli d tau, plus I got to add in the initial voltage from that previous region, which was 100 millivolts. Okay. And the result of that integral is 100T minus 100 millivolts. And that's the equation of this line. 100T minus 100 millivolts. The equation of that line is 100T minus 100 millivolts. That's for T greater than or equal to 2 milliseconds. Yes. Great question, Liz. So if I evaluate this, I get 100 milli tau evaluated from 2 milli to T. So when I substitute in, I get 100 milli T minus 200 milli. I think I have my multiplier wrong. Wait a minute. Is it minus? Plus 100. Yeah, that's what it is. You see that? And I think the milli should be there, though, because I think I'm milling twice. But it should be in millivolts. Yes?
What is it when it's hot to?
It is. So it's continuous. It's got to be because it's a capacitor. So right at 2 milliseconds, it's 100 millivolts. And because it's voltage, it has to be continuous. So whether I stick it in this formula or that formula, it better give me 100 right there. Okay, I want to do one more thing and then we're moving on from this problem. But are there any questions about what we have so far? I want to know what the energy is at 5 milliseconds. I want to find the energy in the capacitor at 5 milliseconds. The energy in the capacitor at 5 milliseconds. How could I find the energy in the capacitor at 5 milliseconds? The energy in the capacitor at 5 milliseconds. So I need to find the voltage at 5 milliseconds and square it. I need to find the voltage at 5 milliseconds and square it. What's the voltage at 5 milliseconds? 500 millivolts. Is that right? So Liz, what I'm going to do is stick a 5 in 100T minus 100 millivolts. So 5 times 100 is 500 milli, but you got to subtract off the 100. So this is actually 400 milli, right? Everybody get out your handy dandy calculator and tell me what the energy would be at 5 milliseconds. What's the energy at 5 milliseconds? Do it in your head or get out your handy dandy calculator from Blue's Clues. What is the energy at 5 milliseconds? What is the energy at 5 milliseconds? What is the energy at 5 milliseconds? Taha? Yes? I don't even know if this is right. Ethan, don't write that down. Okay, are we good? I'm moving on. I don't know if it's right or not. Is that what you two got? 80 microjoules. Micro is times 10 to the negative 6. Okay, all right. Page 7, page 7. Skip page 7, it shouldn't be there. Page, whatever this is. So lecture 1-2. Let's talk about series and parallel inductors and capacitors. Inductors in series combine like resistors in series. So you just add them together, and if they have an initial current, the combined inductance should have that same current because they're all in series. They should have the same initial current. Inductors in parallel combine like resistors in parallel. which means it's 1 over the reciprocal of the sum of the reciprocals, right? So 1 over L equivalent is equal to 1 over L1 plus 1 over L2, and so on. If they're in parallel and each inductor has an initial current, then the net inductance should be the sum of all the currents because it has to obey KCL, right? And that's the only way to obey KCL. So if I put them all together, then I of T naught should be the sum of all the currents. Okay? Inductors combine like resistors. Any questions about that? Okay, page 2. Page 2. If you have zero initial conditions, then there's also a voltage and current divider. So if you don't have any stored current in the inductor, you can use the voltage divider and the current divider, and the voltage and current divider look exactly like they do for resistors. There is one typo here. This denominator should be L sub n. So if you have resistors inductors in series, you can use the voltage divider. If you have inductors in parallel, you can use the current divider. So remember, voltage divider is for series. Current divider is for parallel because the voltage divider is based upon KVL or a loop, and the current divider is based upon KCL or nodes. Voltage divider series, current divider parallel. That's KVL and KCL. So now that we know everything we need to know about inductors, I want you to tell me what the net equivalent inductance is for that network in example 1. What's the net equivalent inductance for the network in example 1? When we combine inductors, just like we do with resistors, you work from the outside in, the outside to the network, to the terminals. So you want to start with 6 in parallel with 14 and work your way in. So you want to start with 6 in parallel with 14. With 6 in parallel with 14. 4.2, very good. And then those are in series. So the next step is you're going to put those in series. 4.2 and 15.8. Winning. Very good. So then you're going to have 20 Henry in parallel with 60 Henry. 20 Henry in parallel with 60 Henry. 15? 15, okay. So then you're going to have 5 Henry in series with 15 Henry. 5 in series with 15. 20, okay. And now we have 60 in parallel with 20. Is it 60 in parallel with 20?
It should be 80.
Oh, thank you. Thank you. 80 in parallel with 20. Thank you, Shayna. 80 in parallel with 20. 16, very good. So then we have 16 in series with 24. 16 in series with 24. 40. All right, I'm gonna let you guys finish. I think you can do it from there. We have 12 Henry in series with 10 Henry in parallel with 40 Henry. What is the net inductance seen through terminals A and B? The net inductance seen at terminals A and B. 20 Henry. Very good. You're going to have 12 and 8. So Annika says that it is 20 Henry. How many people agree with Annika? Very good. Okay.